So welcome to the last session of Eurocrypt on fully homomorphic encryption. The first talk is accelerating BGV bootstrapping for large P using null polynomial over ZPE by Xiema, Terong Wang, Anyu Wang, and Xiang Wang, and the talk will be given by Xiema.
Hello everyone, I'm Shihema from Tsinghua University, and I will talk about our paper on BGV bootstrapping with large P. I will first introduce some background on FHE and BGV, and then I will describe some existing BGV bootstrapping methods and their limitations. Finally, I will introduce our methods and contributions. So the concept of fully homomorphic encryption was first proposed by Rivest, Edelman, and Dertudes in 1978, and it allows anyone to compute unencrypted data without the access to the decryption key. The first FHE scheme was designed by Gentry in 2009. The BGV scheme is an RLW-based FHE scheme designed by Breakersky, Gentry, Microtanathan in 2011. We denote the M's cyclotomic ring as R and its quotient ring modulo Q as RQ. The plaintext modulus is a prime power, P to the power R, and a plaintext polynomial M is an element of RPR. The BGV scheme is suitable for computing on modular integers and finite fields. We also give the encryption and the decryption algorithms here, and the important thing is that the RLW error, E, is multiplied with the plaintext modulus before being added to the message. And an important feature of BGV and BFV is called plaintext batching, and this is achieved by an isomorphism from the plaintext space RPR to L copies of E, where E is some Galois field or ring with an extension degree of D. Each of these L positions is called a slot, and then the homomorphic operations enjoy the symmetry property, which means the homomorphic additions and multiplications are both slot-wise. Another very important method in FHE is called bootstrapping. Because our currently known FHE schemes rely on noise encryption. So as the homomorphic computation proceeds, the noise will accumulate and finally grow so large that decryption may fail. And the idea of bootstrapping is to homomorphically evaluate the decryption circuit, which will also reset the noise level in the ciphertext. And this will allow for infinite homomorphic computations. However, the bootstrapping is much more expensive than the regular homomorphic arithmetic operations, and it is the performance bottleneck of all FHE schemes. For BGV bootstrapping, we need to evaluate the BGV decryption circuit homomorphically, and we have two cases here. The first case is called the general bootstrapping, and where each slot stores a finite field or ring element. The procedure is given in the figure. So first we use decryption formula simplification to increase the plaintext modulus to P to the power E. And this step also introduces an error epsilon to the plaintext polynomial. In the next step, we use a linear transformation to move the noisy coefficients of the plaintext polynomial into the slots. After that, we use homomorphic digit removal to remove the noise part epsilon and to recover the message coefficients mi. Finally, we move mi from the slots to coefficients with another linear transformation. And the performance bottleneck here is the homomorphic digit removal. And in the second case, which it is called thin bootstrapping, each slot stores an integer instead of a finite field element. And the bootstrapping procedure is similar to the general bootstrapping case, so I will not go over it again. And still the performance bottleneck is the homomorphic digit removal. So what does this homomorphic digit removal does, it extracts the highest RPI digits, which are the message, and discards the lowest E minus R digits, which are the noise. And it is an iterative process, and the basic operation in it is called digit extraction, which keeps the lowest PI digits and sets all the other digits to 0. There has been numerous studies on improving the efficiency of this basic operation. For example, in HS15 and HS21, they compute a lifting polynomial of degree p repeatedly for E minus 1 times. And in CH18, they replace it with a single lifting polynomial of degree p minus 1 times E minus 1 plus 1. And in GITV23, they decompose the polynomial from CH18 into 2 or more sub-polynomials with much lower degree, but at the cost of more level consumption. So as we can see, in these words, the polynomial degree is at least p. So when p is large, the digit removal and the BGV bootstrapping may be inefficient. And that may explain why p is chosen to be at most 257 in the previous words. And our idea is to accelerate BGV bootstrapping with null polynomials. First, we introduce the definition from GITV23 of null polynomial. A polynomial f in ZPX is called a null polynomial over some subset S of ZPE if for every point in S it evaluates to 0. And this notion was first exploited by Heelan et al. At Eurocrypt 23 to accelerate digit removal. Since the digit removal is a series of homomorphic polynomial evaluations, so suppose we want to compute a polynomial f on an encryption of A. If we try and find a null polynomial g over the support of A, then we can reduce f modulo g to get a new polynomial. And this polynomial is functionally equivalent with f because at every point in the support of A, its evaluation is the same as f. However, since we have reduced the modulo g, it may have a lower degree, which means we can spend less time and level to compute it. So our target now is to find low degree null polynomials. And we provide 2 approaches to achieve this goal. The first one is based on the observation that the size of the error term epsilon can be made very small. And as a consequence, we can have a low degree null polynomial over p to the power E minus R times mi plus epsilon I. And we look at the first steps in BGV bootstrapping. We begin with ciphertext encrypting M. We multiply it by p to the power E minus R. And after that, the message will have its lowest E minus R PI digits equal to 0. Then we raise the modulus to a very large one, which we call BQ. This step will fill the lowest PI digits with the error term, epsilon, and which we rename it as I. The reason will be explained at the end of this presentation. And I is exactly the overflow part of the second RLW ciphertext with respect to its ciphertext modulus small q. And with a heuristic by Halevi and Shope, we can bound the sides of the coefficients of I with the following equation, where omega m is the number of distinct prime factors in M. As we can see, the bound is very heavily dependent on the Hamming-Weight H of the secret key. So a natural idea is to use the sparse secret key encapsulation technique by Boltzmann et al. To get a very small I, and that is to say we switch to a very sparse bootstrapping key before going into bootstrapping. And for our concrete parameters, the size of I is about 23. So let's now construct the null polynomials. We define S to be the support of p to the power E minus R times mi plus ii, and we let B be the bound on the error term I. We have the following polynomial lambda x, which is a null polynomial over S of degree at most e divided by e minus r times 2e plus 1. Since its degree is no longer linear in P, as in the previous methods, so when P is large, this degree can be much smaller than P. For example, with P equal to 2 to the power 16 plus 1 and R equal to 1, its degree is less than 100. And the idea of constructing lambda x can be roughly understood as this. We looked at the smaller polynomial, the product of x minus I, with I ranging from minus b to b. Its evaluation value at every point in S is divisible by p to the power e minus r. So if we compute the product of many copies of this small polynomial, then the resulting polynomial, when evaluated at every point in S, will be divisible by p to the power e, which just means that it is a null polynomial over S. Now we apply the null polynomial to the digit removal. And we consider two cases. The first case is where the error term I has only one p-array digit. So now extracting the lowest p-array digit will just remove the I and finishes the digit removal step. And we can directly apply the null polynomial in this case. And in the second case, if I has two p-array digits, we follow the traditional digit removal algorithms to remove the two digits one by one iteratively. The red arrow stands for polynomial evaluations that can be accelerated with the null polynomials, and the black arrows means linear combinations. We know that we do not consider the cases where I has more than two digits because now we already support for a wide range of p, with p no more than or no less than 11. And if I has more than two digits, the p will be too small in that case, so that the degree of our null polynomial may be higher than the original digit extraction polynomials, and they will be ineffective. And here is the second approach for constructing null polynomials. It is based on a technique from KDE plus 24. And we can transform the input to digit removal into the form of I plus delta I prime, where both I and I prime are bounded by B and independent of M. As a consequence, we have a null polynomial of degree 2b plus 1 squared over the coefficients of I plus delta I prime. However, the null polynomials constructed in this case usually have higher degrees than those in the first approach. Let's look at the figure. So with the technique from KDE plus 24, we compute two ciphertexts. The first one encrypting delta I plus I, the second one encrypting I plus delta I prime. And we use homomorphic linear transformations and digit removal on the second ciphertext to get the encryption of I. And finally, we subtract I from delta I plus I to recover M. And there are two choices for the integer delta. We can choose it to be a power of p or an integer coprime with p. And in the first case, where delta is a power of p, the digit removal procedure is identical to that in our first approach. And the only difference here is we construct the null polynomials in a different way. So let's look at the values in the box. These values have support sizes no more than 2b plus 1 squared. So for every value a in this box, we have the very natural null polynomial lambda ax. In the second case, where delta is coprime with p, we additionally require that b plus delta b is less than half of p. And we can have an interpolation polynomial fx of degree 2b plus 1 squared minus 1, which can compute a modular reduction against delta on the coefficients of I plus delta I prime. We note that in this case, the plaintext modulus during bootstrapping will remain p to the power of r because delta is coprime with p. And this may save some extra modulus during bootstrapping. And here are our parameter sets. And we mainly focus on 3 columns. The first column is the plaintext modulus, which has the prime p increasing from the first to the last parameter set. The second one is the Hamming weight of the bootstrapping tree, which is very low. And the third column is b, the bound on the error term I, which is also very small since we have a very small h. And we compare the degree of polynomials used in digit removal in both hlib and our method. The first parameter set has 3 numbers in it because the error term I has 2 p-array digits, and we need to compute 3 polynomials to complete a digit removal. And for other parameter sets, there's only 1 number because I has only 1 digit and can be computed with a single polynomial. And as you can see, the polynomial degree in our methods are much lower than that in the hlib methods, especially when the p is very large. And here are our experimental results. We mainly focus on the performance of the digit removal step. Because the polynomial degrees in digit removal is now much lower than the original one, so the time to compute the digit removal and the modulus spent in computing it both decreases. And these 2 factors together increase the bootstrapping throughput, which can be as large as 150 times compared to the original one, and in the parameter set with the largest p. And to summarize our idea, the sparsity of I in the input to the homomorphic digit removal allows us to construct null polynomial of degree roughly 2 times the bound of I times z divided by e minus r. A similar idea has already been used in Ckks bootstrapping, where they begin with Q0I plus m and compute a modular reduction against Q0 to recover m. And if the size of I is small in Ckks bootstrapping, they can approximate the modular reduction function on a smaller range, which means lower polynomial degree. So in both BGV and Ckks bootstrapping, the term I has the same expression as a function of the Hamming weight, and both schemes benefit from a sparse bootstrapping tree. And this is exactly why we have renamed the error term epsilon to I, because we want to show the connection between Ckks bootstrapping. And thank you for your listening.
So are there any questions?
Hi, thank you very much for your talk. I want to ask, because I could see that you've compared to implementations in hlib. Did you do any comparisons with the previous work by Galen et al.?
No, we thought about comparing with it, but I didn't find the implementation first because I was looking at the ePrinter version and not the publication version. And another point is that we have to rely on the sparse secret key encapsulation technique for our efficiency, and while they don't need it, so we need to make some modifications before we can compare. So no, we didn't compare with it.
Okay, thank you.
No more questions? So let's thank the speaker again. The next talk is Bootstrapping Bits with Ckks by Yung Bin Bae, Yung H. Chown, Yaong Kim, and Damien Stellé. And Damien will give the talk.
Thank you, Jean-Sébastien. Okay, so I'm going to present the paper briefly. If you want more details, the paper is on ePrint, so 2024-767. Okay, so let me delve in. Okay, so this is the takeaway from the talk. Ckks can be efficient for binary circuits, and the amortized cost in single-thread CPU for a binary gate is 70 microseconds. And how do we achieve this? So we design a dedicated bootstrapping algorithms for messages that encode bits. Okay, so a few reminders on Ckks. So the native plain text of the native clear text of Ckks are vectors of complex numbers, and the dimension of the vectors is somewhere from 2 to the 13 to 2 to the 15. And the native operations that you have homomorphically for Ckks are additions of those vectors, component-wise multiplication, component-wise conjugation, and you can take the coordinates of the vector and rotate the coordinates by 1 and put the last coordinate in the first spot. It's very efficient. So the amortized cost in GPU for a multiplication is 75 nanoseconds. So the question that we may have is why not using this super efficient FHE scheme for handling discrete data? Okay, so in the rest of the talk, I'm not going to give timings in GPU. I'm going to focus on single-thread CPU to compare apples to apples. But if you want to sync GPU in your head, you just take the CPU timings and divide by 100. Okay, so why discrete data? So there is a bunch of good reasons to look at discrete data. So to handle databases, financial transactions, or to homomorphically implement cryptographic primitives, which has a bunch of applications such as transciphering or also like thresholdizing different cryptographic functions. And the common belief is that if you want to do binary operations, you should use DM or CGGI, also called TFHE. If you want to do computations on approximation to real numbers, you should be using Ckks. So maybe that's the overall rule of thumb if you ask people about the status of FHE today. And I will show in the next few slides that I mean, it's not so simple. So there was a breakthrough result this year by Drucker, Moshkovich, Peleg, and Scholl, who explained how to use Ckks to do exact computations. So in particular, binary computation. So they do a bit more than binary, but in particular, they focus on binary. So to encode a bit B, which is 0 or 1, they just view the bit as a real number. So 0 is going to 0 as a real number, and 1 is going to 1. And because you have real numbers, in the translation, you are adding errors. So 0 becomes 0 plus epsilon, 1 becomes 1 plus epsilon for a very small epsilon. So this format, interestingly, is compatible with binary gates. So here I take the example of the OR gate. So if you want to add B1 and B2, you can do B1 plus B2 minus B1, B2 over the integers. So I don't know, if you take 1 and 1, for example, it's 1 plus 1 minus 1, it's 1. It's indeed the OR of 1 and 1. And this you can, this bivariate polynomial, you can just use over the reals on B1 plus epsilon 1 and B2 plus epsilon 2, and that gives you something which is close to B1 plus B2 minus B1, B2, so it's close to the OR of B1 and B2. So this, you can evaluate binary gates like this, and in fact, OR is not like a weird example. All symmetric binary gates can be implemented with multiplication depths equal to 1. So you may realize that the more you compute, the larger epsilon gets. So in the previous slide, the shape of the new epsilon is pretty disgusting, and it's actually bigger than the previous the epsilons of the inputs. And if the epsilon grows too much, then the B becomes ill-defined. So if I give you a value which is very close to 1/2, at some stage you don't know if it's 0 or if it's 1. So it's becoming too noisy, and you are losing sense in your computation. So what they do to handle this is to use what they call a noise cleaning polynomial or noise cleaning function, which is 3x2 minus 2x cubed. So it's a funky way to evaluate the identity function, because it's mapped 0 to 0 and 1 to 1. But interestingly, the derivative in 0 and the derivative in 1, these two derivatives are 0. So that means that 0 is not just mapped to 0, but 0 plus epsilon is actually mapped to 0 plus epsilon square. And 1 plus epsilon is actually mapped to 1 plus epsilon square. So the epsilon is being squared, so the noise is cleaned. Okay? And once you have cleaned the noise, you can keep computing. Okay, so what do we do based on this? So DMPS uses Ckks in a black box manner, so they don't go into the innards of Ckks. They use it just based on the usual user interface. And what we do is that we open the box. So in particular, we design a bootstrapping algorithm specifically for the DMPS format. So if you remember, the DMPS format, it's a vector of complex numbers that correspond to bits, so zeros and ones, up to some noise terms. Okay. So now we have to go into bootstrapping. I'm not going to do reminders on the whole Ckks bootstrapping because it's pretty hairy and we don't need it. At some stage in Ckks bootstrapping, there is an eval mode step, and that's what we are going to look at. So eval mode is doing the following. So this is on regular ciphertext. Eval mode takes an m plus q0i, where q0 is a so-called bottom modulus, and I is some integer. And this m plus q0i should be mapped to m. Okay. So it's a mod 1 function, if you want. If m is a real, you are removing a multiple of q0, so it's a mod q0 function. Mod q0. But one difficulty is that we can only evaluate polynomials. So we can do addition and multiplications, but mod 1 or mod q0 is not even a continuous function. So in Ckks bootstrapping, to do this, there are two steps, at least for syncing. So one is to first replace x by x to x mod 1 by a trigonometric function, which is a good approximation to the mod 1 function around integer points. So it's replacing the blue curve by the red curve. And the second step, because sine is still not a polynomial, is to replace the trigonometric function by a polynomial approximation to it. And on the picture, you can't see it because the polynomial is so close to the trigonometric function that it's also the red curve. Okay, so we evaluate mod 1 by a polynomial approximation to a trigonometric function on a given number of periods. Okay, so here is the main observation. In eval mode, you are trying to map 1 over q0 m plus I to 1 over q0 m. If m is real, is an arbitrary real number, mod 1 should be approximated on fairly wide intervals, whereas if m is a bit, mod 1 can be approximated on a discrete set, because you know that m is either 0 or 1. Okay, and if m, in fact, it's not quite true because the bit is coming with noise. So if m is a bit, mod 1 can be approximated on very narrow intervals. So we have smaller intervals for the approximation, which sounds good, but we have actually twice more of them if we count. So maybe it's not so easy. So let's see how we do it. So on the left, you have the regular eval mode. With the approximation, and the approximation should be good on the light blue intervals. And on the right, you have the modified eval mode, where the approximation should be good on points that are very close to either integers for bit 0 or non-integer half integers for bit equal to 1. Okay? So as you can see, the red curve on the left and the blue curve on the right, they are both trigonometric functions. And it turns out that the blue one is just a shifted scaled version of the red one. But we are interested in the blue one only for x's that are of the form b over 2 plus epsilon for a bit b, for b equals 0 or 1. Okay, so that's a zoom in of the new eval mode. So z, as you can see, is being mapped to 0. So 0 is sent to 0. Z plus a half is being mapped to 1. So 1 is being sent to 1. So it's correct. And an interesting point is that it's almost the same function as before. So it's as efficient. And it's super easy to implement. So that's a nice bonus for the experiments. OK, so why is it a good modification of eval mode? So there is a first good reason. As you can see, the derivative in the z points and in the z plus 1/2 points, these derivatives are 0. So it not only bootstraps, but it cleans the noise at the same time for the same cost. So bootstrapping and clean at the same time, which is a nice first bonus. Second aspect, even more important, is that the message is encoded as b/2 plus epsilon plus an integer. So b, the important part of the message, is the most significant bit after the rounding point, after the integer point. Whereas in regular Ckks, you have 1 over Q0m plus I, where 1 over Q0m is much smaller than 1, because you want a good approximation of the mod 1 function by the sinus function. And you need the input of the sign to be very close to an integer in this case. So in regular Ckks, 1 over Q0m is much smaller than 1. And in this gap, so this gap is about 10 bits in practice. So this gap means that you need to work with precision, I don't know, maybe 5 bits to represent m, 10 bits of gap between m and the integers, and 5 bits for I. Whereas in the new eval mode, we have maybe 5 bits for b/2 plus epsilon, so we have a good approximation to a bit, and 5 bits for I. So 10 bits now compared to 20 bits before. So it doesn't sound that much, but it's actually a gigantic, I mean, it helps gigantically, because this allows to reduce the primes that are used in bootstrapping, so the sizes of the bootstrapping levels. And this is multiplied by the number of levels in bootstrapping. So I don't know, if you use 10 levels to bootstrap, this gain of 10 bits, it's multiplied by 10. So it's 100 bits that are saved that you can use for actual computations. Okay, so what does it give experimentally? So here, as I said, I'm looking at single-thread CPU for comparing apples to apples, and I'm looking at amortized time per binary gate. So if you look at DM-CGGI, I mean, the rough order of magnitude these days is 10 milliseconds. So some works go a bit below, maybe 7, 6 milliseconds. DMPS, our naive implementation of DMPS was around 100 microseconds. And DMPS with our bootstrapping, the timings that we get is 17.6 microseconds per gate, per binary gate. Okay, so you may say, okay, but there is a catch here. It's amortized. Because amortized actually is amortized over quite a bunch of binary gates. So in particular, it's amortized over all the slots. And if you remember, the dimension of the vectors is somewhere between 2 to the 13 and 2 to the 15. So it's being amortized over many, many binary gates. So if we want to compare DM-CGGI versus Ckks, so in terms of throughput, our algorithm is much better. So it's 17 microseconds versus 10.5 milliseconds. So it's much, much faster. In terms of latency, the comparison goes the other way, because CGGI bootstrap a single gate in 10 milliseconds. So it's still 10 milliseconds, where our bootstrapping, for the parameters that we chose for this experiment, it takes 23.1 seconds. So you have to wait longer, but once you waited the 23 seconds, you bootstrapped like 2 to the 15 gates. So overall, it seems that for heavily parallel computations, you better use Ckks. For non-parallel computations, you better use DM-CGGI. And what is the limit? So to try to assess the limit, we designed another parameter set for Ckks for the following experiment. So we want to bootstrap DM-CGGI with Ckks. So how do we do it? So as inputs, we get many DM-CGGI ciphertexts, which are LW ciphertexts. We glue them together into a single Ckks ciphertext. So we go from many LWEs to one ring LWE. So this is a step called ring packing, for which we have very efficient algorithms. Then, once it's in the Ckks format, we use our Ckks, our binary or bit Ckks bootstrapping. And after it has been bootstrapped, we convert back to the DM-CGGI, so we go back from ring LWE to LWE, and that step is actually very simple. It's just reading the entries of the ring LWE ciphertext. Okay, so that's the experiment that we do. So it turns out that for the parameters that we optimize for this, if you have about 170 DM-CGGI ciphertext to bootstraps, you better use Ckks. So below 170, just use DMCGGI. Above 170 gates, switch to Ckks to make it faster. Okay, so wrapping up, Ckks can be used efficiently for binary circuits. For throughput, it's close to 1,000 times faster than DMCGGI. For latency, one way to handle latency is with the experiments of bypassing DMCGGI bootstrapping by using Ckks. If you have 170 parallel gates to do, you better use DMCGGI. If you have below 170 gates to perform, you better stick to, no, below 170, you better stick to DMCGGI. Above 170, you better go for Ckks. Okay, if you have any questions, feel free to ask. And if you want to know what these figures mean, I send you to the draft, to the paper. Thank you for your attention.
So, are there any questions?
Thank you for the talk and very interesting work. In case of DM and CGGI, it can be extended to the larger inputs like ternary or larger than. Have you ever considered extending it to the larger inputs?
So, okay, so indeed, our work is only bits. And a natural question is to extend to small bit length integers. So there is something about it in the DMPS paper. I think there is a paper by you also to evaluate gates for small bit length integers. So what I can reply in terms of bootstrapping is stay tuned, something is coming. Yeah.
Thank you.
Hey, thanks for your talk. I was also attending the previous talk on the INCPAD model, so I would like to ask you about the parameters and the expected p-error probability of incorrect evaluation in this case, whether this would be usable with the INCPAD oracle.
Yeah, so indeed. So I gave a talk on Saturday on INCPAD insecurity of some exact schemes, including this one. So if you're interested in INCPAD security, you need a very, very small failure of bootstrapping in particular for Ckks. So in this case, we didn't fix it here. So we focused on INCPA security. And the failure probability is, I would say, the usual one for Ckks bootstrapping, at least in our library, around 2 to the minus 50.
Okay, thanks.
So it's not small enough. It's not crazy small, crazy large, but it's not small enough for INCPAD.
Thanks.
Thanks for the talk. So I was wondering, there's another line of work that uses approximations on multi-intervals. So you have a lot of disjoint intervals where you approximate the function. So have you explored that and contrast that with the approach that uses the sine function?
Yeah, so we try to do these things like I mean when it comes to polynomial, I mean the function that we want to evaluate is meaningful only on very few intervals. So the best we could think of is to try to find a smallest degree polynomial that correctly approximate exactly on this union of intervals. So we tried. I mean in our case, it was not very successful. So I cannot formally say why. I don't have a good intuition as to why. But going via the trigonometric function helped a lot.
Thanks.
That's all I can say. It's not very satisfactory, but.
Okay, so let's thank the speaker again. The next talk of the session is Circuit Bootstrapping Faster and Smaller by Rudy Wang, Yundi Wen, Zai Li, Zheong Lu, Benqiang Wei, Kun Liu, and Kunpeng Wang, and Ruida Wang will give the talk.
Okay, thank you very much. I'm Ruida Wang from Institute of Information Engineering, Chinese Academy of Science. And today I will talk about my paper, Circuit Bootstrapping Faster and Smaller. Let's start with a little bit background. First, the fully homomorphic encryption allows computations on encrypted data without decryption. So this property is suitable or available for applications such as secure cloud computing and privacy-preserving machine learning and so on. So there is a typical client server model of the FHE delegate computing. Maybe the client have some sensitive data of healthcare or finance or even government. He can encrypt the data using fully homomorphic encryption and transfer them to the cloud server. Then the server will process the data under encryption and give back the ciphertext result. The client will decrypt to obtain the result. Okay. Damien and Shihema already told us some about BFV and Ckks, and our work is focused on few anti-FHE schemes. I think these two schemes are somewhat alike, so there is also a unified framework proposed by Michel Angel in 2021. And these two schemes are known for their bootstrapping efficiency. For example, the gate bootstrapping in TFHE RS of Dama only cost maybe 7 milliseconds, and the gate bootstrapping of our in our light FHE library only maybe 4 microseconds. So we submit this result to Ckks. For milliseconds, sorry, I make a mistake. Maybe I'm trying too hard to outperform Damien's work in my dream. Okay. Let's continue to talk about Few and TFHE bootstrapping. In fact, there are two evaluation modes in Few-like crypto systems. The first is the fully homomorphic evaluation mode. It means that we do bootstrapping gate by gate. And there are lots of work focused on this area to improve the efficiency or functionality of gate bootstrapping. For example, functional bootstrapping, multi-value functional bootstrapping, full domain functional bootstrapping, private functional bootstrapping, and so on. But there is also a poor and sleepy field in field-like crypto systems, is the leveled homomorphic evaluation mode. This mode means that we can evaluate a large-scale circuit without bootstrapping, and then perform the circuit bootstrapping. So I will introduce an example of a lookup table without bootstrapping, and then introduce the circuit bootstrapping. The lookup table is evaluated through the Semiox gate. We put the formulas in the right corner. And if we want to perform the functions f0 to f31 on x0 to x7, it means maybe 8 input and 32 output lookup tables. Then we should pack these truth table values into RLWE ciphertext T0 to T7. And we can use the RGSW input x7 to choose the RLWE ciphertext. For example, in the first Semiox gate, if x7 is 0, then the first Semiox gate will output RLWE T0 instead of RLWE T1. And in the fourth, maybe the fourth Semiox gate, it will output RLWE T6 instead of RLWE T7. After performing such a Semiox tree, then we can find the block contains the correct answer. And then we can use x0 to x4 to blend rotate the correct answer into the first 32 terms of the plaintext polynomial. And then finally, we can extract them into 32 LWE ciphertext. So the circuit evaluation converts the input low noise RGSW ciphertext to high noise LWE ciphertext. It leaves us two difficulties. The first is the noise management, and the second is to realize the circuit composability. In fact, the circuit is evaluated very fast. Maybe a gate is only 100 macrosecond. Oh, this is right, macrosecond. But however, the circuit bootstrapping is very expensive because it aims to refresh the noise first, and it also need to convert the ciphertext from LWE to RGSW. So how to construct an RGSW ciphertext? An RGSW ciphertext consists of two decomposed RLWE ciphertexts. So if we want to do circuit bootstrapping, we should begin with a high noise LWE and to construct these two gadget RLWEs. Then I will introduce the original ideas of the circuit bootstrapping and our improved circuit bootstrapping. Okay. The original ideas uses functional bootstrapping or multi-value functional bootstrapping to reflect the noise, and then use a private key switching to convert from LW ciphertext to gadget RLW ciphertext. Although the simple extraction is almost for free, but the repacking from LW ciphertext to the RLW ciphertext is expensive. So the conversion step accounts for more than 70% of the circuit bootstrapping times. So our idea is a conversion over the polynomial ring. Then we can avoid switching between LWE and RLWE and RLWE and RLWE. Okay. So and we can use NTT, the number theorem transform, to accelerate the polynomial multiplications. Okay, but there is a key problem. The key problem is that if we do not use simple extract to extract the LWE ciphertext from the RLWE ciphertext, then there will be some redundant terms after blend rotation. Like this, there are some redundant power of x. Our solution is to introduce homomorphic trees evaluation to turn these terms to 0. The right corner is the trace property. You see that you can remove some power of x terms. And we want to speed up the homomorphic trees evaluation, so we use the tower case decomposition to decompose homomorphic trees evaluation from n times homomorphic automorphisms to log n times homomorphic automorphisms. As a result, the conversion over the polynomial ring can make the circuit bootstrapping faster and smaller. We can reduce the computational complexity of circuit bootstrapping from O(n) squared to O(n) log n squared. And we can reduce the key size from O(n) squared log q to O(n) log n log q. Yeah. Furthermore, we also proposed an automorphism-based circuit bootstrapping. So we should begin with an automorphism-based blend rotation. You know, the key procedure of blend rotation is to homomorphically evaluate sigma AISI modulo 2n. So LMKC proposed a method that we can choose some O numbers from Z to n and then convert the operations from an additive group to a multiplicative group. Then sigma AISI modulo 2n can be calculated in these formulas. We can map these elements to the power of x, and then the multiplications are homomorphic evaluated by homomorphic automorphisms. Yeah. So our improved method is very straightforward. We can choose some more sparse numbers. That means that we can convert operations to a new multiplicative group. And this group is only generated by one generator G. And then the formula is like this. Okay. So the first advantages is that we need to perform less homomorphic automorphisms to implement the blend rotation. And there is also a key there is also the sparse blend rotation also implies multi-value functional bootstrappings, and it's necessary for us to accelerate circuit bootstrapping. So this is our we propose the first multi-value functional bootstrapping based on homomorphic automorphisms. Yeah. Okay. Let's see the performance. Now our code is available on GitHub, and this is some parameters, and we acknowledge Dr. Jin-Cho Ha from KIST, who provide us a tighter noise analyzation. So we adjust the parameters and give the new performance like this. Okay, our work is 7 times faster than the TFHE method, and our key size is 5 times smaller than the TFHE circuit bootstrapping. And if we compare it with the pre-processing circuit bootstrapping, then our work is also 3 times faster than this method, and the key size is 25 times smaller. Okay, so finally, I will maybe leave some discussions. First, the TFHE library, TFHE PP, and MOSFHET implement circuit bootstrapping via AVX FFT. And we will also soon release our code, our circuit bootstrapping via AVX NTT. Yeah. And I think we need more work to further VCAP this sleepy field. For example, the batching method, like batching gate bootstrapping. But a batching circuit bootstrapping maybe is not the key problem. The key problem is how to use a batched RGSW to lookup table. Yeah. And there are maybe some other potential applications like transcephering, like TT network, specking network. Okay, that's all of my presentations, and thank you very much.
Yeah, any questions?
Thank you for the nice talk. So since the TFHE gate bootstrapping also uses blind rotation,
yeah.
So I was wondering if your technique can apply to that and give a speed up as well.
You say the second improvement, right?
Right.
Yeah, it can also use for gate bootstrapping, but the parameter citing is very tight, so the speed up is not very obvious. Yeah.
I see. And a quick follow-up is that, so for the 2 different techniques you mentioned, could you comment on about what percentage do they contribute to the overall speed up?
Okay, maybe the main speed up is the first improvement. Yeah, it's a conversion over the polynomial ring. And if you use automorphism-based blend rotation, then it's benefit for the key size, but not the efficiency.
I see. Thank you.
Thank you.
Any more questions? No, so let's thank the speaker again. So the last talk of the session is FHE Beyond NCCA Security by Marc Manoulis and Jérôme Nguyen. And Jérôme Nguyen will give the talk.
Right. Hi, everyone. Thank you for your presentation, introduction. Yeah, I'm Jérôme. I'm going to talk about the security guarantees of FHE, what we can expect, what we maybe should hope for, and what lies beyond in CCA1 security. So maybe a very quick history. So since Gentry's breakthrough paper that introduced bootstrapping, there have been many, many improvements since then, making FHE much more efficient, much more useful in practice. But from a security standpoint, it was essentially only considered in the context of chosen plaintext attacks. So this was probably very reasonable to start with, because FHE was, as I said, very inefficient anyways. So all these like stronger security models might not have been so relevant. And maybe if you think about the most obvious application, which was outsourced computation, it wasn't quite clear if it really needed something stronger. Okay, also, I sometimes think that it also was because, well, it just seemed pretty hard of a problem to get something stronger, because FHE seems inherently vulnerable to CCA attacks, chosen ciphertext attacks. Okay, but maybe CPA is actually enough in practice. Maybe we don't need to bother. And I would maybe somewhat provocatively say no. And maybe more conservatively, I would say it depends. But okay, maybe I can convince you that we had this attacks on approximate FHE schemes by Liam and Chancho. Since then, there have actually been also attacks on exact FHE schemes, whatever that really means. There are also some ciphertext validity attacks, where you have an oracle that tells you if a ciphertext is valid or not. So this is called usually the CCVA model or CVA model. There's a paper by Shilotti and all. Also this client-aided outsourcing setting where the server gets help from the client during the computation of the homomorphic evaluation by sending it back to the client. The client decrypts, re-encrypts, sends it back, so essentially you don't have to bootstrap. Yeah, this was introduced by Agrawal and all, and they gave a model that represented this, the FunkCPA model. So this is non-exhaustive, but this might already be enough to consider that maybe we really should think about stronger security notions for FHE. And maybe we can hope for something a little bit more robust that isn't so application dependent. Right, so if we were talking about regular encryption, we would obviously look at CCA2 security, so adaptive chosen ciphertext security. This essentially implies all the nice properties, security properties that we want out of an encryption scheme. And I'm sure you all know this, but this is the normal indistinguishability game. The adversary gets to choose two messages. One is encrypted and gets sent back as a challenge ciphertext, and the adversary needs to decide which message it encrypts. So in the CCA2 game, you get two decryption oracles, one before the challenge ciphertext, which has no restrictions, and one after receiving the challenge ciphertext. And this one has one restriction that I'd like to highlight here. It's you are not allowed to decrypt the challenge ciphertext. Right? So this is to avoid trivial attacks. Well, fortunately, maybe it's well known that homomorphic schemes are totally incompatible with CCA2 security notions, and so in particular FHE2. You can always take the challenge ciphertext, re-randomize it by adding some kind of other ciphertext that encrypts maybe a 0 or something like that. You get a new ciphertext, so you can decrypt it, and then you get the actual plain text, so obviously you win. Right? So this is not possible. Okay, what about CCA1, so the non-adaptive version of this? So this is exactly the same game. Again, distinguishability kind of problem for the adversary. And now he only gets the decryption oracle in the first phase. In the second phase, he gets nothing. Right? And kind of conceptually, you can think of it as exactly the same game as CCA2, but the kind of restriction we had on the decryption oracle is now much increased. It's essentially for every ciphertext. And I'll highlight this because what we're going to do later on is kind of try to modulate this restriction. So if one extreme is the CCA2 game and the other is the CCA1, we're going to try to find a middle ground. Okay, so what about CCA1 for FHE schemes? Well, there are some positive results for general FHE, and by this I mean FHE schemes that do not use bootstrapping. And so this is quite unpractical because we don't really know how to actually get schemes like this, apart from maybe leveled FHE schemes. But okay, this is maybe not quite satisfactory. And for bootstrapping schemes, there is this kind of folklore result that says that it cannot be done. And this comes from this reasoning that, okay, the bootstrapping key is public. The bootstrapping is the encryption of a secret key in some way, and you have a decryption oracle. So you can decrypt it, you get the secret key, you win. So at least if you do it in a straightforward way, it doesn't seem like you should be able to get CCA1 security. So this kind of gave us this interesting question that, okay, we just saw that general FHE lives in this CCA1 world. Schemes that use bootstrapping lives in this CPA world. But we'd like something stronger. Can we get something that is CCA1 with bootstrapping key? Can we get something even stronger? That's essentially what we're going to try to do. And yes, this is possible. So we do define, we do propose a notion we call INT-VCCA, so for indistinguishability against verified chosen ciphertext attacks. So as kind of hinted at, it's going to be between CCA1 and CCA2 security. It is the strongest among the known achievable notions for FHE. So we compare it with some of the other notions I talked about earlier. And we also give an equivalent formulation in the non-malleability kind of formulation of security games. So we call it targeted non-malleability VCCA. And this is actually a generalization from a paper from Bonnet and al. In 2011 where they did this, but in a CPA and CCA1 context. Yes, so we show that this is actually achievable. You can build it in at least the random oracle model, and you, as promised, can do it for schemes that use bootstrapping. And we do this from some passively secure FHE schemes, so CPA or maybe CPAD, with or without bootstrapping, but probably with. Some kind of general CCA2 transformation that I'm going to explain in a second, and succinct non-interactive argument of knowledge, a SNARK. Right, but before showing you the construction, I'm going to explain a little bit more about the VCCA notion. So the issue is, as we've seen before, that when you're trying to define a stronger security notion, you hit kind of a wall where if you have an evaluated ciphertext, so something obtained through homomorphic computation, the oracle can't really tell, well, where it came from. Is it something totally legitimate? Has the challenge ciphertext been used to obtain it? You can't really tell, right? But what if you could? Very maybe naive idea. What if you could tell? What if you had some sort of algorithm that kind of reversed this, kind of allowed you to access some sort of history of the ciphertext and was able to tell you, okay, this ciphertext has been obtained through this homomorphic computation from these original ciphertexts. And if we add a few other kind of requirements, we want that these outputs are going to be fresh ciphertext. By this, I mean that they have just been output by the encryption algorithm. And if we have this thing called soundness, which essentially means that the extraction works as kind of expected. If you decrypt the C hat, you obtain the same thing as if we applied F on the decryption of the ciphertext. Then we kind of have something that allows us to really detect any homomorphism. And by this, I even mean additive homomorphism, which usually is quite hard to see, maybe. And this is actually enough to give us a nice security notions. We just describe a new oracle, a decryption oracle. And as I said, it's the same decryption oracle, essentially, but we kind of changed the restriction on it. So instead of just checking if it's a challenge ciphertext, we first extract the query, see where it came from, have this history, right? And see if the challenge ciphertext is among these. If it's not, we decrypt, and if it is, well, we refuse to decrypt, obviously. Yeah, so then we can just plug it into our indistinguishability game. So as I said, it's exactly the same game. But instead of having in the second phase this normal decryption oracle, we have this now VCCA oracle, right? Apart from that, nothing has changed. This is actually enough to obtain some nice properties for our FHE scheme. So we are able to show all these implications. So all these security notions I talked about in the beginning, the CCA1 security, the CCVA, the FuncCPA, this is all with it. It also implies HCCA notions, which I didn't explain about, and I won't because of the time. But it is essentially some sort of notion for homomorphic encryption, but only for univariate functions. yeah, so as I said, there is this equivalent formulation, the TNM VCCA, which I also won't explain. But yeah, so as you see, we have the CCA2, which is out of a big picture for FHE, and then we're above kind of all the other security notions. Okay, so how do we build this? How do we achieve it? Is it even possible? So we do it in 2 steps. First, we use, as I said, a CCA2 transformation to totally break the homomorphism of our FHE schemes. I'm using this pretty unclean notation to signify that CCA2 of M is some kind of CCA2 ciphertext encrypting M. And we want to have some specific kind of structure to it. So if anchor of M at the bottom here is the FHE encryption, so the actual homomorphic encryption, we want the CCA2 of M to actually have this part that's still homomorphic, and something on the side, right, that kind of makes it CCA2. Right? But we still want to have access to this homomorphic part. So maybe this is more clear if I give some examples. So for the symmetric FHE case, you could use encrypt then MAC. So you have the homomorphic encryption C prime on the side and then a MAC. Or you could encrypt then sign. This is also possible actually in the symmetric setting. In the asymmetric setting, you could use something like the Naur-Jung transform, which is essentially you encrypt the same message twice. So we would do it with the actual homomorphic encryption, and then you prove that this is all consistent, it all works out, C1 corresponds to C2, and there's no issue. What you can't do is using, for example, the Fujisaki Okamoto, because it doesn't have this structure I was talking about with having the homomorphic ciphertext on one side and something separate on the other side. Okay? So I did promise that we could do bootstrapping. And in fact, we don't need to do anything to get bootstrapping. What's very important is once you have a bootstrapping key, do not release the actual CCA2 ciphertext, right? We're using this transformation to kind of tell the decryption what is a valid ciphertext, what is not. So obviously, you want the bootstrapping key to remain not valid. So you just leave it as it is. Okay? Now for the second part of the transformation, we're going to use a snark to prove 2 things. So first is we're going to prove that we know the CCA2 ciphertext that we want to use in the computation. Right? So on one side, we're going to prove, okay, I have this C1 CL. I know the corresponding T1 TL that makes it CCA2. That's the first thing. The second thing is we're going to prove that we evaluated correctly. So our C hat as an output is actually the result of the correct evaluation of the function that you claim with the ciphertext that you claimed you knew the CCA2 version of them. Right? And this is actually all we do. It's quite conceptually easy, at least. In practice, it might be more difficult. We do need some quite strong properties that I'm not going to talk much more about in the interest of time. But all we really need is so that we want some kind of extractor for the snark that is non-rewinding, simulation extractable in black box. And it is possible, it exists. There have been some construction in the random oracle model. So that's why we need the random oracle model. Yes, so kind of to put it together, see why we actually obtain VCCA security. Well, as I said, so this is kind of the workflow of FHE computations. You encrypt stuff, you evaluate it, and you send it to decryption, and hopefully you get your function applied on the messages. And okay, so the adversary gets kind of 2 points where it can attack. So on one side, it's the encryption part of it, right, where you could mess at this point, maybe mess with the C1 ciphertext, and this kind of gets propagated all the way through the chain, so through the evaluation, and then when you decrypt, it's going to result in some kind of attack vector for the adversary. Right? So that's why we used the CCA2 transform. So this is kind of excluded. You can't mess with the first part anymore. But the adversary still can mess with the evaluation algorithm. Right? So even though you send kind of legitimate ciphertext and everything is good, if the evaluation didn't work out, well then the C hat could still be unlegitimate, and when you decrypt, the adversary still gets his attack through. Right? So that's why we used the snark to kind of prove that the C hat came from the CCA2 ciphertext, and everything went well through the evaluation algorithm. And so you kind of propagate the security of the CCA2 through the evaluation algorithm to the C-hat. Now, when you decrypt, you should be sure, after verifying that the proof is correct and everything went well, that you would obtain F of your messages and all you want. Right, so this is actually all you need. So this is actually VCCA secure, we show that. And kind of to give a proof idea, I mean, as I said, you reduce it to a CCA2 security. And in the reduction, you answer every decryption query by extracting each query, so with the extractor from the snark. All right. So to conclude, we proposed a new security notion that is the in-VCCA notion that is actually achievable for FHE schemes through generic transformation in the random oracle model, and this is maybe more importantly allows for schemes that use bootstrapping, and it is the strongest achievable security notions for FHE. At least it was at the time of writing. I've been made aware that there has been a paper released on ePrint 2 days ago that might extend this somewhat. All right, thank you very much for your attention. I'd be very happy to answer any question you may have.
So, any questions? No question. So I have a question. So how compact is the resulting ciphertext, including the?
Yeah. So if you use so we have this notion that I didn't talk about, where you can do the CCA2 transform in a publicly verifiable way, right? Like so that you can verify the validity of a ciphertext publicly. Then the snark can prove the validity of a ciphertext, and then it can be totally compact. It's only the size of a proof, right? If you don't use that, so for example, if you encrypt the MAC, where you can't verify if you don't have the secret key, then you need to actually send the ciphertext with it. It kind of needs to follow everything, and then it's not very compact in the sense that it's linear in the input size of the evaluation function.
Okay, thank you. Mm-hmm. No questions? So let's thank the speaker again. So this is the end of the session.